I think we are streaming, though we still have a minute or so to go for the start time. Okay, Rajaram, if you would like to start, we are online and it is also time. Yeah.
Okay.
Perfect.
Okay. So here we are in the fourth lecture, which is going to be very focused on closure quantities, as the summary put up at the beginning says. And closure quantities have been around a long time, but mainly in the case of so-called copolar interferometry, right? Where it's assumed, and it's an accurate assumption, that you are correlating the same polarization in all the antennas. And then you're essentially dealing with one electric field component, and the correlation is a scalar quantity. Okay, we'll see how that works as a warm-up for doing it in full polarization. And that's a relatively recent topic. Started, to my knowledge, around 2020. And that's also been one in which, with very able collaborators, I've been involved. And it's maybe of all the things I've talked about, this is the most contemporary. So the background is that, of course, synthesis imaging works with correlations, which are really called visibilities, based on some phrase coined by Michelson, fringe visibilities. And you measure them at different projected baselines. And at least with the help of Earth rotation and large numbers of antennas, you hope that you've filled in this baseline space, which is called the UV plane. And then you Fourier transform with respect to U and V. The conjugate variables are two direction cosines, and you get a map. Now, this is the scalar or copolar case. And the map is the intensity in that polarization. And of course, if the source is unpolarized, then that's just the Stokes I. But we have also seen, in particular, in the last lecture, when I referred to the early work at the Owens Valley interferometer and showed you this black box equation, that in full polarization observations, the correlation between antennas A and B becomes a 2x2 complex matrix. We'll write it down. So then when you Fourier transform that, you get an image of each Stokes parameter in the sky. Okay. So this is what it looks like in mathematical terms. Okay. So all important averaging sign. This looks very much like the definition of Stokes parameters, but the vital difference is that this pair of electric field components is sitting at antenna A, and this pair is sitting at antenna B. Okay. And you're forming all four products by taking this outer product, and you're averaging. Averaging over many inverse bandwidths, all right? But for, in fact, this entire lecture, I will be thinking of what is called a snapshot. We're not going to wait. We're certainly going to wait many inverse bandwidths so that this average is meaningful. But we're not going to wait so long that the orientation of the antennas with respect to the source has changed sufficiently that all these quantities have changed. Okay. So that's the framework in which we are working. And this matrix has been written as in the same form that we wrote the Stokes parameters at a single antenna, right? I plus Q, etc., etc. But there is an important distinction. Okay. There is no reason why, for example, the product of these two should be real, because EA comes from one antenna and EB star comes from another. Right? In fact, it's really the Fourier transform of I, Fourier transform back from the sky to the baseline space, which is what is sitting here. Likewise for Q, U, and V. So although it looks like the matrix we wrote down for Stokes parameters. This is really something different. It's called a Stokes visibility. And the important thing is that these diagonal elements are not real. And these two off-diagonal elements are not complex conjugates of each other. Right? It's a general 4x4 complex matrix at a given baseline. Okay. So, of course, synthesis imaging goes on with various processes. Now, in the traditional approach, without using closure quantities or anything like that, one tries to calibrate the instrumental response. Okay. And by going to a calibrator, and if you're able to quickly go to the calibrator and come back before the calibration has changed, okay, it may even allow for propagation effects in the ionosphere and so on. Okay. And ideally, you would like point sources. And if you want to calibrate the polarization response of the feeds, then you need a polarized point source. And you also need to observe it as the polarization rotates with respect to your antenna feeds. And that is a topic extensively dealt with in the references that I put up last time. Okay. And we will also be working in the framework. And this takes care of a large fraction of the effects. That these are antenna specific. So at a given antenna, the incoming electric fields are modified in a very specific way that we will see. Now, of course, you apply this calibration and you still have the problem that the visibilities do not cover the entire UV plane. And this problem, perhaps the one person who did not face it was the pioneer of aperture synthesis, Martin Ryle, because he had the advantage that, he was the first and only one in the world. So he patiently moved his telescopes till they filled the UV plane, okay? And I think I've heard from people that he, in fact, did not approve of people who would leave gaps in the UV plane and cover those gaps by deconvolution, okay? But, the radical of one age is the conservative of the next age. And even in Martin Ryle's group, people like Steve Gull and so on started playing these dangerous games. And of course, when the Westerbork telescope was filled, a successor to the Cambridge telescope, so to speak, they cheerfully left gaps in the UV plane, and they had to pay a price for it. When they back Fourier transformed the visibilities of a point source, they got a nice ring around the point source. And they said, okay, we will deal with it by something called clean, which had been invented by them. It worked. There is one interesting case, I can dig it out if someone is interested, where they were imaging a supernova remnant which happened to agree with this ring. So part of it was reconstructed as a point source at the center. But I mean, barring such accidents, they were able to. And by the time the VLA was designed, the next great successor, it was assumed that this process would take place. Cleaning the most popular algorithm. But these algorithms go by the general name of deconvolution. And well, I gave an entire Govind Swarup Memorial lecture on imaging. But so this statement is somewhat tongue-in-cheek. Deconvolution is a polite way of saying that you don't have data which fill the Fourier plane. You create an image nevertheless. You transform it back, and it agrees with what measurements you have, but it also produces measurements where you have no measurements. So clearly, there's some magic going on in the deconvolution process, and many people, including me in collaboration with Ramesh Narayan and others, have worried as to what exactly is this magic. So I'm just calling it prejudice. In any case, this process applied alone before 1980s gave maps with a dynamic range of 100. Dynamic range being, let's say you had a strong source, and then, because your calibration is not perfect, you will still get artifacts due to this small source and strong. And actually, it's a very good engineering if you can get it down to 100, right? It means all effects are at the 1% level, right? And that was the situation pre-1980. And I am old enough to remember when Ron Eakers visited RRI in 1979, he was moving from Westerbork to the VLA as its director. And he gave specifications. His lecture was called "The VLA Goes into Operation." And the specifications, I mean, the National Radio Astronomy Observatory got $80 million to build a telescope which would achieve this dynamic range. Because at that time, there were lots of problems where you could do interesting things with this dynamic range. Ryle, in his Nobel lecture, which is really worth reading, he also takes a look at the future. And he's very well aware of these propagation effects, right? Which at low frequencies, the ionosphere, at high frequencies, water vapor. And he says, yes, we can do something, but there are limits. But then something dramatic happened. Okay, I call it the self-calibration revolution. And maybe it illustrates the fact that necessity is the mother of invention. Okay, so there were two areas in which it was absolutely vital to do something about this problem. A very long baseline interferometry. And there, of course, getting the phase is really very hard. In addition to the fact that, you have very different atmospheres or ionospheres over the two telescopes. The fact is that they're running on independent local oscillators. And however good they are, their relative phases will drift on some time scale. So VLBI people initially were just living with visibility amplitudes, okay? But definitely difficult to pin down. The other context in which people had to think about this problem is called Merlin. Merlin stands for Multi-Element Radio-Linked Interferometer. Now, of course, the legend of radio astronomy that the Cambridge group under Ryle, created aperture synthesis and showed the whole world how to do it. And that was in the 60s. And maybe in the 70s, the rival group, or let's say the other group in UK, which is Bank, who were famous for having this very large dish, right? Decided they would get into this game. Actually, they did a lot of early interferometry as well, but right now, Merlin was radio-linked. So it had long baselines all over Britain, okay? They had these dishes at centimeter wavelengths, and they could correlate, but the phases were really not pinned down, okay? So then two independent groups, Conwell, Wilkinson at Bank and Schwab at NRAO, invented what we now call self-calibration. I'll tell you very briefly what it is. It happened in 1981, and it completely changed the scene. And today, everyone uses it. Right? Everyone. And again, somewhat tongue-in-cheek, the philosophy behind self-cal is the following. One is already solving for missing visibilities, right? And your deconvolutional algorithm is doing that. Perhaps if you are thinking of the clean algorithm, by subtracting point sources, and there are some other algorithms as well, which put in different kinds of models for the source. So with the help of these models, you're solving for missing visibilities, and which could be easily of the same order as the measured visibility. So of the order of n squared, right? N is the number of antennas. But you also have these n unknown antenna-based gains. So in the scalar or copolar case, it's one complex number at each antenna. Now, if you can use the deconvolutional algorithm to tell you something about, n squared missing visibilities, surely it can tell you something about n antenna-based gains. So this was the idea behind self-cal, right? Which actually Conwell and Wilkinson called Cortel, correction at individual telescopes. And Schwab, I think, called it global fringe fitting, but in any case, okay? So that's a brief account of self-cal, and I'm not going deeper into it because in some sense, the closure quantities I'm going to talk about really come into play when this doesn't work, and we'll see that, right? So when self-cal is good, it is very, very good. I don't have to tell the users that. And the dynamic ranges went up dramatically by a couple of orders of magnitude. Okay. And of course, that's history. Therefore, the VLA produced amazing results. In fact, the same Ron Akers, who went to VLA as its first director, has also speculated in Westerbork, why did we not invent self-cap, right? He said it's because our engineers were so good, right? That we felt we didn't need to, tweak what they did. But it has its limitations. When data is sparse, it doesn't work that well. And of course, with telescopes like the VLA, the data is not that sparse, right? And even very long baseline interferometry, VLBA and so on, there's a large number of antennas. But now we're skipping over many decades, right? If you take the most extreme form of aperture synthesis that has ever been done, extreme in terms of wavelength, because this is now 1.3 millimeters, and extreme in terms of baselines, 10,000 kilometers. So I'm kind of assuming that everyone has heard of the Event Horizon Telescope. Basically, this amazing collaboration across the Atlantic. So Max Planck and Cambridge, Massachusetts, that group being the kind of anchors, but they gather large collaboration around them. And in particular, they managed to persuade the directors of many, many millimeter wave telescopes, which are in different continents and, had, completely different kinds of systems, probably spoke even different languages, to participate in this experiment. So I think the final collaboration has some 340 members, which is still small compared to LIGO or the collaboration which worked on the Higgs boson, but it's an impressive number for radio astronomy. And their first images, which came out in 2019, I think, of the innermost region of the M87 active galaxy, the radio, what you see in radio. And as you go to shorter and shorter wavelengths, the innermost region, which is optically thick, starts showing up. And of course, the outer regions start disappearing because they have very steep spectra. Okay. And I mean, this is an amazing image. And soon after, they came with the polarization images. So these lines are really polarization. And the 4 images are actually on 4 different days. And that has something to do with the physics. When you're so close to the black hole, things can be changing on the time scale of days. If you think that is short, you should think of the other source which they imaged, which is Sagittarius A, which has a similar angular diameter because it's much closer, has a much lower mass black hole. And there the time scale is minutes. So anyway, let's not get into such difficult problems. But it's also true that each one of these images is an average or some, it's derived from some 4 other images. Now, the reason why they did that is precisely what I told you, that they had multiple and independent teams make images by different methods with different pipelines. One is, of course, that they were making such a strong claim of seeing the innermost region on the same scale as the event horizon. And the other reason is that the data was still not that extensive that one could just pin down the image by the traditional methods. Okay. So, of course, many innovations in imaging are there in the HT papers. But amongst those innovations, the one that we will focus on are what are called closure quantities. Now, before actually telling you what closure quantities are, I'm going to take a small algebraic digression. Okay, you can call it a parable. So let's say you have 2 equations and 3 unknowns. X plus y plus z is 1, x minus 3y plus 2z is 3. So clearly, you're not going to get the values of x, y, and z. But suppose z is something that you're not that interested in. It's some nuisance. Okay, but it is your measurements are 1 and 3, what you're really interested in are X and Y, and of course, you're not going to get them, right? But then you say, what's the best statement I can make about X and Y? And the answer is, use this equation, call Z 1 minus X minus Y, push it into the second equation, right? And if I've done the algebra right, you will get a relationship between X and Y, eliminating the nuisance parameter Z, okay? So if you have parameters which you're not really interested in, like the gains, right? But they are coming in the way of your measuring what you want to measure, then you can still eliminate those gains and obtain, of course, not the full solution, but you can obtain information connecting the measured parameters to the unknown parameters. That's the moral of this little algebraic story. Okay. So now we have n into n minus 1 by 2 baselines, but each gives you a complex visibility, right? So multiplying that by 2, we are always going to count real parameters. So that is what we have. The measured visibilities have so many real parameters. And of course, the true visibilities also have the same number of real parameters. Okay. However, the true visibilities are related to the measured visibilities in a way that we will write down very soon. And they have been corrupted by n complex gains. Okay. And that should have been 2n real parameters, but I've removed one. And the reason to remove that one is, if you think of these complex numbers multiplying the electric field at all the antennas, okay, the scalar electric field, because only one feed, only one polarization, then you can shift all the complex numbers by a common phase, and that will not affect the visibilities. You'll still get the true visibilities, because every visibility has a GA and a GB star. So if the same phase is applied to GA and GB, then so the right count is 2n minus 1. Okay. So we are in a similar situation that you have more unknowns than equations. Okay. So just to make this a little more concrete, think of a very hypothetical radio telescope which has 30 antennas, right? So n into n minus 1 is, I think, 870, right? And 2n minus 1 is 59. Okay. So you have 59 visibilities. I'm sorry, 870 real parameters in the visibilities which you'd like to measure. You make 870 measurements, but they are corrupted by 59 unknowns. Okay. So what the best you can hope for is to get, let's see, 870 minus 59 is 811 relations between your measurements and your unknowns. Okay. Now, that's not too bad, because you have, 870 unknowns, and you've learned, something about 811 combinations of them. Okay. So that's the general concept of closure quantities. Elimination of the unknown gains, right? And you get a smaller number. So now let's see how this works out in practice. And actually, from the earliest days of radio astronomy, ingenious ways were found by ingenious people to cancel these antenna-dependent complex gains by forming appropriate combinations of the measured visibilities. So they're basically of two kinds. So here is what happens to the electric field at a given antenna. Okay. So antenna A, S stands for what comes from the sky. GA is the complex gain sitting at that antenna. And therefore, the measured electric field is the product. Okay. Now, the visibility is, of course, the average of the product of two electric fields, one of them complex conjugated. So I've written it out. And you notice I've also put the average sign inside. So one is assuming that these gains are not fluctuating on your integration time scale. Okay. So what you have sandwiched between this J and GB star is the true visibility, right? So that's what's written out. So basically, this is the structure of the equations which connect the true visibilities, unknown, the gains, also unknown, and the measurements. The measurements which are known. So Jennison at Jodrell Bank in 1958. So this was their early interferometry. It was very simple compared to it. They would just take a few antennas and move them out into the countryside, okay, with radio links and so on. So he had this inspiration of forming this product of three visibilities around a triangle. Okay. So we measured AB, we measured BC, we measured CA. And we use this relationship between measured and true visibilities from the ones from the sky. So sure. And the cleverness of this is, of course, that here A is occurring in the first slot and here A is occurring in the second slot. So you have a GA and a GA star. Likewise, the GB and the GB star. Likewise, GC and GC star. So you're not got rid of the G's completely. However, you have certainly got rid of the phases of the G's, right? So this quantity, the string of 6 G's is real. So this equation really tells you that the phase of this triple product of true visibilities is the same as the phase of the triple product of measured visibilities. So you've learned something about the true visibilities. And this is called a closure phase. Okay. Jennison is quite a remarkable man. He visited the Raman Institute and he, in fact, gave a lecture on the origin of inertia. So he's clearly a man of broader interest than just radio astronomy. And he has a unique distinction. The Raman Institute auditorium has a large, long table behind which the lecturer sits and a gigantic blackboard. And I think Jennison is the only person I know who actually lay down on that table to make some point in his lecture. So that is Jennison. And soon after, in Australia this time, these three authors came up with closure amplitude. So this is a combination of 4 visibilities. So look on the left, measured visibility on AB, CD, divided by measured visibility on AD and CB. And the cleverness here is that, of course, the A occurs in the same slot, the first slot, in the numerator and denominator. So the GA cancels. And likewise for B, C, and D. So this combination of 4 measured visibilities has exactly the same value as the same combination of, and this is with amplitude and phase. Okay. So this is called a closure amplitude. Now, so you need basically triangles to compute the closure phase, and you need quadrilaterals to compute the closure amplitude. Now, one can try to count how many of these there are. The number of baselines sort of scales as n squared. The number of triangles grows as n cubed. The number of quadrilaterals grows into the 4. I mean, you can write down more accurate formulae like n into n minus 1 into n minus 2 into n minus 3 divided by 24 and so on, but basically scaling as n raised to 4. So clearly, it's overkill to use all triangles or all quadrilaterals because you'll be manufacturing many more quantities than even the measurements, okay? So they surely cannot be independent. So what you would really like is to find an independent set of triangles and independent set of quadrilaterals. Right? Now, in the case of triangles, one can do the following. And you can take triangles which all share a common vertex. So you keep A fixed. And you form, if you have some 3 other, you can have ABC, that's one triangle, ACD is another triangle, and ADB is a third triangle. And I'm going to show you a sketch which shows that having these 3 triangles, you can construct a triangle of BCD. So in other words, you can construct any other triangle not involving A. Okay. So you just have to imagine that you traverse the triangle from A to B, B to C, C to A, then back from A to C, C to D, D to A, then again back from A to D, D to B, and then back. So you notice that all the baselines which originate from A and go to these three vertices are traversed twice in opposite directions. And there's this standard property of visibilities that the visibility phase changes if you traverse the antenna in the opposite. Basically, you you move the star to the other antenna. Okay. So therefore, the phases on these three baselines disappear, and what you get is the closure phase on BCD. Okay. So therefore, you just remove A. So you have n-1 antennas, and you have n-1 into n-2 over two baselines, right? And each of those baselines gives you a closure phase, and those closure phases are enough to construct any other closure phase. So this is the count of the number of closure phases. So you would think that, yes, people therefore had some similar way of exhibiting all the closure amplitudes. But surprisingly, that didn't happen. Okay. So let's go back to the first argument I'm going to give you. Just counting the number of closure amplitudes is the one given in this Bible of synthesis imaging called, it's called TMS for Thomson, Moran, Swenson. It's a great book. But when it comes to actually giving you the number of closure amplitudes, this is the kind of argument they give. The same argument we said about eliminating the G's, right? So we had n squared minus n, real parameters. But then we had 2n-1 G's to be eliminated. And therefore, the number of identities or combinations, or whatever you like, relations, you get is n squared minus 3n plus 1. And you can quickly check that if you put n equal to 30, you get 811 in this equation. All right. So now you say, okay, this is the total number of invariants, even though we don't have them. We just counted them. Okay. We already have n-1 into n-1 over 2 closure phases. So this must be the number of closure amplitudes. Okay. They also cite a paper by Lannes, which is a very mathematical paper. It's from France. I suspect that paper is more cited than read. I did read it. It's a very nice paper. It has some fairly sophisticated mathematics in it. However, I could be wrong, and someone might tell me that there is a direct construction of independent quadrilaterals. Okay, but the first one that I have seen, and I have to say it's the referee who pointed it out to us. So it's very elegant, and it's from a paper from the HT group, and it's 2019. So of course, the theme of this paper is also to look at the noise properties of these closure amplitudes, right? Which also tells you that the HT took closure amplitudes very seriously, right? But you can read this paper. By the way, all these references will be put up, or maybe, yeah. So this is Blackburn and Company. Now, this is not absolutely essential, but one can also think of think of these invariants. I'm using the word invariant rather than closure. Invariant simply means that you have eliminated the gains. So, okay, so there are combinations of measured visibilities which have eliminated the gains. So therefore, they are essentially functions of the true visibilities. Okay. So measured visibilities, as before, we have seen. So think of measured visibilities as a point in 870 dimensional space. That's n into n-1. The true visibility also lives there, right? And if you ask, what are all the possible measured visibilities which can come from this true visibility? Because you don't know the gains, right? So let's say you just apply all possible values of the gains. Then this will spread out into 2n-1 dimensions. So 59 dimensions in our example. Okay. So every true visibility belongs to a kind of sheet, if you like. And the mathematicians call it a foliation or something. And this sheet is 2n-1 dimensional, so 59 dimensional, right? And that represents all the possible measured visibilities that you might get, depending on the values of gain, from this one true visibility. So this entire space is filled with these 2n-1 dimensional objects. So you've still learned a lot about, let's say you are somewhere on the sheet, right? You measure and somewhere on the sheet, you at least know that you're not on some other sheet. Okay. So you've learned something about the true visibility. Okay. And so if you think of introducing coordinates in the space, you could have 59 coordinates on the sheet and then 811 coordinates which go away from this sheet. Okay. And those coordinates obviously are constant on the sheet, right? So they are your invariants. I mean, that's one way of thinking about it. There's also this jargon of codimension, right? So if you have, a 59-dimensional object sitting in a 870-dimensional space, then its codimension is 811. So that's all there is to it, and that gives the number of invariants. But as I said, this is not a construction. This is an existence proof. But this is the argument that one can think geometrically. This geometric picture actually will come out to be useful later. Okay. So now let's get into imaging with closure quantities, scalar case to start with. So the early efforts in VLBI, you couldn't really make an image, but you said, okay, this is some superluminal source. Maybe it has one blob and another blob and maybe a jet. So you try to play with those parameters and see if it fits the visibility amplitudes. And later on, whether it fits the closure phases and closure amplitudes. So this is what is called forward modeling. You don't try to go from the data to the image. You have models of the image which have parameters, and you compare them to the data in the data plane, which is always a good thing to do. And you try and infer these parameters. If you get a good fit, of course, then you're happy. Now, in some sense, you could say self-cal does that, except it does it in a very automatic way through the deconvolution algorithm. And I do want to emphasize to all the fans of self-cal that if it converges, if it's independent of the initial guess, and it finally converges to within the noise, then there is absolutely no need for closure quantities. Okay. And the reason is that if you ignore the noise, you've come up with an image, it predicts Fourier components, right? And if you apply the gains, whatever gains have come out of self-cal, to those predicted Fourier components, they agree with the measured. So you've automatically satisfied all the closure quantities. Okay. But as I told you, especially in the EHT context and perhaps in some other contexts, this doesn't work if the data is sparse, so on, right? And that is when one gets interested in closure quantities, either from forward modeling or there are courageous people who have said, okay, you've already seen that these closure quantities are very nonlinear in these Fourier components. So you can't just transform back. But, if you are clever enough, you could come up with some algorithm, which you start with some image points. And I mean, you could say fit, but you try to set their values in such a way that they're consistent with the closure quantities. And although this is one of the most recent papers, I remember a very early one by Shevgaonkar, whom, maybe many old timers may know, who did some radio astronomy and IA and RRI. And this is actually part of his thesis, but of course, things have moved on a lot. This is a very nice paper on what you could do with just closure quantities. So closure quantities are of interest. And if you're interested in polarization, so finally at slide 11, polarization is going to appear. Okay. As I said, work on this started in 2020. These are the collaborators, more or less in chronological order. So N stands for Nityananda Tyagarajan. So when I give his full name, I have to say he's no relation. But actually, there is a relationship. He did a project on deconvolution, actually, in NCRA when he was studying engineering in IIT Madras. Okay. And when we started this collaboration, he was at the VLA. And then he is now in Perth. Okay. Joseph Samuel, RRI and ICTS, Vinay Kumar, ICTS. And now everything's a matrix. Okay. The electric fields are 2x1 matrices. Their adjoints are same complex numbers written in a 1x2 matrix. The Stokes visibility is the average. And this is measured. This is the known quantity because this is what you measure and you form the Stokes visibility. But unfortunately, your EA measure is related to EA from the sky by an unknown 8-parameter complex matrix. Okay. Likewise, the EB, the field landing on antenna B, is modified by another complex matrix. And now we better keep the order right. Okay, these are matrices. So this is the way it should be written out. When you take the dagger, the order gets interchanged. Right? So G times E becomes E dagger times G dagger. And now, of course, this refers to antenna B. And what you have sandwiched between these two gain matrices is the true visibility, which comes from the sky. Okay, so this looks very much like what we had in the copolar case. Okay, in fact, I used little letters there, and now they are capital and boldface. And the equation looks exactly the same, but it's not exactly the same because these are matrices. You can't indiscriminately move them around the way that we did with complex numbers. Okay, so that's what made this an interesting problem, and perhaps that's maybe no one had a shot at it. So anyway, Nitya and I, as part of keeping occupied in COVID, we started on this problem. And the first progress came from defining something called a hat. A hat is just R notation, right? So take a matrix, take its dagger, and also take its inverse. And actually, you can do it in the opposite order also. It doesn't matter. Okay, you can check. Now, A hat has a nice property, which neither dagger nor inverse has. When you take a dagger or an inverse, the order gets reversed. But when you take both, the order remains the same. So there is one nice property of A hat. It does not reverse the order of a product. But the property which makes it very useful for cancelling gains, for constructing invariants, is this. So look at a product which has alternate hats. So you have VAB, then you have VBC with a hat. Now, why do you need the hat? Suppose you just wrote VAB into VBC. The VAB would end with a GB dagger. Okay, but the VBC would begin with a GB. Okay, and the GB and GB dagger don't cancel. However, if you take the hat of anything, right? Suppose you take the hat of VBC. First of all, the order doesn't change, right? But so VBC begins with a GB, but when you take the hat, it becomes GB dagger inverse. And now VAB ends with a GB dagger. So you've actually achieved your goal of cancelling GB. Similarly, of course, once you have a hatted one, you have to follow it with unhatted. Okay, because yeah, you can see that this VBC dagger BC itself ended with a GC hat. With a GC dagger. And when you take the hat, it becomes GC inverse, and VCD starts with a GC. So the rule for cancellation of all intermediate gains is to form products of antennas going, one after sharing one antenna, and products of baselines, and you're able to cancel the intermediate G's. So the idea is to take a product around a loop. And you should take an even numbered loop because you will have a GA on the left and a GA inverse on the right. And people who work with matrices will then, right? Okay, so I have actually written it out in the case of 4. Okay. And, as I said, all the intermediate ones cancel. And if you just keep track, you will see that this ends with a GA inverse and you have a GA. But of course, we essentially had something very similar in the case of, but you can't just cancel these two, right? Can't do that. However, what you can do is that if you take determinant, then you're allowed to move things around. Right? Determinant of product of matrices, the product of the determinants, and it's just a product of complex numbers. So if you take the determinant, these two get cancelled. It's also true that if you take the trace, sum of diagonal elements, they get cancelled. That's a little more subtle. A trace of AB is the same as trace of BA. So now you think of this entire thing as A and this GA inverse as B. So now you're allowed inside the trace to move this GA inverse to the other side and cancel it. Okay. So this is a nice strategy to get invariance. So in fact, it was so nice that we were beaten to it by Broderick and Pesce in 2000. And the way this happened, I mean, not the way they beat us to it, but the way we realized was that Nitya and I arranged a kind of midnight meeting. I mean, it was midnight somewhere, maybe in VLA, and of just friends and relatives, so to speak, right? People whom one had known. And Divya Oberoi was there, and his student was also there. And he quickly came up with this thing which had just appeared in the archive. Okay, so fine. We were scooped on this even-numbered loops and traces and determinants. Strictly speaking, this paper did not have determinants, but it had the trace of inverse. Okay, and you can figure out that actually that's fine. Another way to think about it is that the two eigenvalues of this quadruple product don't change when you hit it with a GA and a GA inverse. So really you have those two complex parameters. You can think of them as two eigenvalues, or trace and determinant, or trace and trace A inverse. All the same. Okay. So that's why my description of this lecture says very clearly that these are the Broderick-Pesce invariants. Of course, for some time one is disappointed, and then one reads it carefully and say there is still something interesting to be done. There's no complete set here. Now, of course, they did try to produce a complete set for 4 antennas. They didn't quite get there. When we looked at it closely, it wasn't. Of course, they deserve full credit for coming up with this concept of. So in the community, these are known as closure traces. Okay. Now, the focus shifted to constructing a complete set of invariants. Okay. So again, the first step is even before you construct them, to count them. Okay. And this will run very much in parallel with what we saw earlier, except now each baseline gives you 8 complex numbers. 8 real numbers, right? 4 times n10 minus 1. And the gains are 1 matrix at each antenna, so 8n. And then as before, you remove the 1. So one of the minor corrections to the Broderick-Pesce paper is that they miss this 1. Okay. So you do the subtraction, and you expect 4n squared minus 12n plus 1 real invariants. So the number of invariants really proliferates, right? Well, of course, you've got much more data coming in, right? But this is not going to help you to construct invariants. So what does one do? Okay. So what I initially did, and Nitya and I sort of kept bouncing it back and forth, was to say, okay, let's take a particular case, like 4 antennas. Let's draw, all kinds of quadrilaterals. And this can be done numerically. You can take random numbers for the visibilities and the gains, right? So you have these invariants. First of all, you can actually check that they are invariants, just numerically, not a problem. But then you can also do something which is inspired by that geometric picture. Okay. So you've got a certain number of invariants. You don't know if they're complete or not. Okay. So you perturb the visibilities in your code. So all the invariants get perturbed. Okay. But if they're not independent, for example, we are talking of small perturbations. So presumably the changes in the invariants are linear. The first term in the Taylor series, so to speak. They're very nonlinear, but in this case, we are looking at the first term in the Taylor series. So now you have these vectors, if you like, which are the changes in the invariants, which occur for various changes in the visibilities. Okay, true visibilities. Now you have a whole bunch of vectors. You can find out the dimension of the space in which they live by stacking them into a matrix and finding the rank. In fact, Broderick and Pesce did this, except they did the rank using Mathematica. But being a kind of poor man, I just did it using Octave and using something called SVD. But in any case, that pretty much gives you the rank. Okay. And then, of course, the rank didn't agree with 4 antennas. You didn't get, 17 invariants. Okay. So you kept throwing in more and more, and we were just struggling, actually. Okay. And that's the point at which Joseph Samuel of RRI joined us. And it's interesting that, of course, I've known Samuel for decades, but it was Nitya who brought him in because Nitya had actually done a postdoc in RRI. So there's some advantage to traveling around. Okay. And his inspiration was to do something which at first sight looks like a backward step. So take this kind of thing, right? It's a triangle based at A. So AB, BC, CA. So very similar to what we did for closure phases. Okay. Except you now have this intermediate hat. So to cancel the gains on B and C, you're still left with the gain on A and G dagger. Now, what do you do with G and G dagger, right? I mean, the usual matrix textbooks will not tell you, but Samuel being amongst his many other achievements, being a card-holding general relativist, and therefore special relativist also, told us, he'd known it for a long time, that if you take any matrix, M, okay, complex 2 into 2, and hit it with this GA and GA dagger, then some combination of the elements in M actually undergo Lorentz transformations. Okay. I'll show you how this happens soon. But at the moment, it now appears that well, they're not entirely Lorentz transformations. We'll see. You also have an overall multiplication. So we'll put that aside for a moment. But that means each M gives you 2 4 vectors. So again, 8 parameters. And then once you have 4 vectors, you can take products of them, dot products, which are invariant under Lorentz transformations. So you've got your invariants. Okay. So now this connection between Lorentz transformations and complex matrices with determinant 1 goes back to the early days of relativity. Okay. But you don't have to go back to those early days because our goal is very limited. The result we need is easy to verify. So here is a general complex matrix, but written more or less as we wrote the Stokes parameters, right? Except you have now T plus Z, T minus Z, X plus IY, X minus IY, and they're all complex, by the way. So the determinant, as we had seen in the case of Stokes parameters, is T squared minus Z squared minus X squared minus Y squared. So long as you preserve the value of this determinant, you're guaranteed that these will undergo Lorentz transformations, T, X, Y, Z, because you're preserving what Einstein told you to preserve in the interval. Okay. Now, of course, you can just multiply it with any matrix with determinant 1, but we are in, right? Now, our matrices GA and GA dagger do not have determinant 1, okay? But that's easily fixed, right? If, it has determinant 2, then you can simply divide both the rows by square root of 2, and it'll then have determinant 1. So really, this T, X, Y, Z don't strictly undergo Lorentz transformations. They undergo Lorentz transformation and scaling by the determinant of G star. And that's a real scaling. That's important. Turns out that in the radio astronomy literature, we were not the first to try and exploit this. There's a nice paper by Britton in 2000. He was largely concerned with a single dish and with pulsar observations. But it's a nice paper. I've thrown in the reference. Okay. And learned of it only later. But of course, our whole idea is to apply it to interferometric observations. So it's also important that if you multiply by a G on the left and a G dagger on the right, is just any matrix with determinant 1 would have done the job of doing a Lorentz transformation. But that would have been a Lorentz transformation on 4 complex numbers, okay? Mixing them up in some strange way. But if you do it this way, then the Lorentz transformation is a real Lorentz transformation. So it doesn't mix the real and imaginary parts of T, X, Y, Z, right? And you have this overall scale factor. Now, with this technology, it was possible to enumerate the invariants and hit the desired number of 4n squared minus 12n plus 1. Okay. And this is there in one of the papers with Sam, myself, and Nitya. Okay. So construct all triangles at a given vertex. Then, as we did in the case of closure phases, take these n-1 into n-2 over 2 baselines which do not include this privileged vertex. And that number is called A. And the name, we had to concoct a name for this because they're not invariant, right? So it was called an advariant, right? And now the first 2 triangles will give you 4 vectors. Already you can do something interesting with them. You can form 10 dot products, each with itself and with the others. So now you have 10 invariants, actually 9 if you take out the scale. But now you have a basis. So now you can project the 2 4 vectors of any later triangle onto these bases. Okay. So after that, you don't need to construct dot products and so on. Once you have the components in the basis. So to cut the long story short, you get 80 minus 7. It is actually 80 minus 6, but you knock off 1 for this overall scale. And 80 minus 7 happens to be this magic number. Okay. And this was exciting. So excited that we sent it to, not to the Astrophysical Journal. I mean, we're a little worried as to what the reaction of Astrophysical Journal would be to this kind of thing. So we sent it to Physical Review letters, and well, at least one referee was excited, and after a bit of persuasion, so that paper, that reference is also there. But this is only the beginning, right? You've got a complete set of invariants for n antennas. What do you do with them? Okay. One of the things which happened, I should say that even before collaborating with me, Nitya was already interested in the copolar case, in particular the closure phases, trying to get some geometric interpretation. So, so he took the lead in applying the same triangles approach to the copolar case, and it unifies. You don't need Lorentz transformation, it's just a scale. And you get the right count, and you get closure amplitudes and closure phases in a unified way. The closure amplitudes are the magnitudes, and the closure phases are the phases of these triple products. Okay, so that's how it happens. Now, ultimately, the goal is, of course, to get images. And I already told you that even in the copolar case, we really stuck for directly interpreting them in the image plane. So what do we do? So with the help of Vinay Kumar, we did some simulations. Okay. And meanwhile, Nitya is exploring AI. And since, you could take the kind of images you're interested in, like rings with polarization and so on, generate these invariants and maybe train, so that's ongoing. Noise properties are important. In fact, we are inverting matrices. So, of course, these are general matrices, and a general matrix, if you just write it down, it could be close to singular. The probability of being exactly singular is 0, which, unless there's some special reason for it to be singular. Okay. So, noise properties have again been explored by Vinay Kumar because he did 2 one-semester projects in ICTS. And then what we did was assuming all baselines are present. So if you represent the antennas by dots and the baselines by lines joining them, you have a graph. And this is the complete graph. So for 4 antennas, it's a tetrahedron and so on. But in real life, you may have an incomplete graph. Some baselines may have very low signal to noise. And I didn't realize this, that in the case of the HT work, they had this JCMT, which has only a single polarization. Okay. So these are sort of generalizations you can look at. And as I said, nothing is complete, but it's ongoing. But of course, the really interesting thing would be to apply to real data. The polarization data from EHT has not yet been released, but I think as per their policies, it will come out. And who knows? Right? Something interesting might emerge from that. But the way I look at it is, we had these closure quantities for decades for copolar observations. So someone should surely get the theory of the fully polarized case into a similar shape. So I'm hoping that we will get into the next edition of Thomson, Moran, and Swenson, but I'm not sure. In any case, that is where matters stand right now. In this, now I've been thinking a lot about how to use the next lecture slot. I promised you, and I think I fulfilled that promise, that this was hardcore radio astronomy, even if somewhat theoretical. In fact, some of you might have thought that you're trapped in the 5th episode of this franchise, which is called The Matrix, right? Now, in the last, I've come up with this following list of topics. And the idea I had in mind was the following, that taking this walk through polarization in radio astronomy, and of course, it's a bigger territory than what I walked through. There are some interesting topics, side topics, which I mentioned, but I didn't really go deeply into. And it could be that some fraction, let me say some non-zero fraction of the audience might find these interesting. I found them interesting. So I didn't say much on how to put an absorbing or lossy system on the Poincare sphere. I did say something about putting something which is unitary, but now it turns out there's a completely independent way that Lorentz transformations enter on the Poincare sphere. And that is, well, let me just leave it at that. You have the celestial sphere, which is light coming from all directions. And if you get into a moving frame, the directions are going to change. So that's a map from the sphere onto itself. Turns out that that's related to these absorbing systems. Okay. So as I said, it's one of those interesting things. There's a formal analogy of polarized light with spin half systems. Okay. So I could state that more explicitly. And then I did mention polarization of the whole sky. And it also has practical applications. And I will mention some of these, which I learned from people like Richard Fisher and Kildall and so on. I may or may not tell you about a non-singular coordinate system over the whole sky because I put up the reference anyway. And then finally, perhaps the most mathematical topic, but which one is quite logically led to if you follow your nose, is this three-dimensional space of polarization and phase, which turns out to be more interesting than just attaching one circle to every point on the Poincare sphere. Okay, so I told you it's twisted in some way, and if one, so I suspect these should keep us occupied on Wednesday, and the time slot, of course, is different. It's more like 4 to 5:30. Okay. So, thank you.
Sorry, Rajaram, 4:30 or 4 here?
See, of course, we never use the last half an hour, but
right, yeah.
Yeah, 4:30 would push it to 6, which may be a bit too late, no?
Okay, so we'll make it because
Oh, sorry.
what I had sent out earlier, I had said 4:30. So I will revise that to 4.
Yeah. Right. Yes.
Sure. Yeah. I'll do that. Yeah. Thanks. Okay. So, yeah, questions or comments? Anyone here? You can just unmute yourself and go ahead. Okay, I don't see any hands or anybody unmuting themselves either. Yeah.
Okay, nothing in the chat.
Yeah, nothing in the chat either. No. Yeah.
Okay. So
yeah.
So that's maybe
Sure.
this.
Yeah. Well, Nitya is there in the audience. If you want to say hi to him, yeah.
Yeah. But he knows all this stuff actually.
Yeah. Absolutely. Yeah. Yeah. Sure. Okay, so then it's time to bring this one to an end, and we meet now on Wednesday at 4 p.m. Right? Yeah.
And of course, now people are very warned as to what they can expect.
What to expect? Yeah, sure. Yeah,
Yeah,
and the slides for the earlier lectures, for the first 3 lectures are already up. The additional material will get there in due course. And I think some of the YouTube or the actually Zoom recordings, the links to those are also up there, yeah, if you would like to take a look. Okay.
Yeah, and even for this lecture, I think I have sent across the slides and the references. I think I have.
Yes. So yeah, we'll get them up tomorrow. Yeah.
Okay, great.
Perfect. Yeah. Okay. Thanks everyone then. Thanks Rajaram. Thanks a lot and see you day after.
Thank you.
Yeah.
Bye.
Bye-bye.
Take care. Yeah.